We're on problem 148. 148. What is the tens digit of positive integer x? We want to know the tens digit. Tens digit. Statement 1 tells us x divided by 100 has a remainder of 30. Well, then we know the tens digit is 3, right? Because let's say 30 divided by 100 has a remainder of 30, and its tens digit is 3. 130 divided by 100 has a remainder of 30, and its remainder is 3. And I can make an argument that any number that when you divide it by 100 that has a remainder of 30, its tens digit is going to be 3. In fact, that number is going to be 3, 0, and then it's going to have a bunch of other digits here, there. And if you just divide this by 100, you're going to be left over with 30. So statement 1 is sufficient to figure out what the tens digit of the number is. Statement 2. X divided by, so we could write x divided by 110 has remainder equal to 30. Well, this is a little different case. So definitely when 30 is divided by 110, the remainder is 30 because it goes into it 0 times. So the remainder is 30. And then the tens digit is 3. But let's see, I'm going to try to find other numbers. When I divide it by 110, its remainder is 30, but its tens digit is something else. So let's see, 140. If I divide that by 110, I'm left with a remainder of 30 of 30. But its tens digit is what? Its tens digit is 4. Right? I shouldn't draw an arrow here. If I did, let's say I go up one more, 250. 250, you divide it by 110, its remainder is 30, but its tens digit is 5. So this statement gives me no information. Saying that the remainder is 30 still gives me no information. The tens digit can be any of these numbers, or a bunch more if I just kept going. So statement 1 is sufficient to answer this question. Question 149. 149. If x, y, and z are positive integers, is x minus y odd? In order for this to happen, one of these have to be odd and one have to be even. And you can just think about that. If you take the difference, or really the sum of two numbers, the only way that that difference or sum is going to be odd is if one is odd and one is even. So let's think about that. Let's look at the statements. Let's see if it gives any information. They say that x is equal to z squared. Well, that still doesn't give me, well, it gives me no information about y. And it gives me actually very little information about x just yet. I mean, it tells me that x is a perfect square, but a perfect square could be odd or even, right? It could be 16, it could be 9. 16 is an even perfect square, and 9 is an odd one. So this doesn't give me much information by itself. Let's see what statement 2 tells us. Statement 2 says that y is equal to z minus 1 squared. So this statement by itself is kind of like statement 1. It just tells me that y is a perfect square of some integer, right? Because z is an integer, so z minus 1 is an integer. So it just tells me y is a perfect square, and a perfect square could be even or odd. But if we take both of these together, then something interesting happens. For example, if we assume that z is odd, then its square will also be odd, right? 3 squared is 9, 7 squared is 49. So if z is odd, then x is odd. And then z minus 1 would be even, and then y would be even. So there would be, one would be odd, one would be even. And you could do the other way. You could say if z is even, x is even. And if z is even, then z minus 1 is odd, and y is odd. And I can prove it to you mathematically. Let's write this with and substitute for z. So x minus y becomes z squared minus z minus 1 squared. And so this becomes z squared minus z squared minus 2z plus 1, and that equals z squared minus z squared plus 2z, right? Distribute the negative sign, plus 2z minus 1. The z squares cancel out, and we're left with 2z minus 1. If we use both statements, x minus y simplifies to 2z minus 1. They told us that z is a positive integer, so this part of the statement right here has to be even. It's a multiple of 2. So this is even. And if you subtract 1 from an even number, this whole expression has to be odd. So both statements together are sufficient to say that x minus y is odd. Next problem. This one looks hairy. 150. Henry purchased 3 items during a sale. He received a 20% discount off the regular price of the most expensive item and a 10% discount off the regular price of the other 2. What was the total amount? Was the total amount of the 3 discounts greater than 15% of the sum of the regular price? Okay. So what was the total amount of the 3 discounts? It was 20% times, let's call X, well, let's just call it item 1. 20% times item 1 plus 10% times item 2 plus 10% times item 3. And 10% times item 3, and I'm assuming this is the most expensive. Let's just say this is second most, I guess. This is third most expensive. Maybe they're the same price, I don't know. And they're asking whether this is the total discount. This isn't what he paid. This is the discount on item 1, the discount on item 2. I'm not saying what they actually paid for item 2. So what the question is, was the total amount of the 3 discounts, that's this number, greater than 15% of the sum of the regular prices? So they're saying, was that greater than 15% of I1 plus I2 plus I3? And I think we can simplify this, because if we distribute this right-hand side, you get 0.15 times I1 plus 0.15 times I2 plus 0.15 times I3. And let's see. If we subtract out 0.15 I1 from both sides, you get 0.2 minus 0.15 is 0.05 I1. And I want to keep everything positive. So let me subtract these from the right-hand side. So I'm going to subtract 0.1 I2 from, so I'm going to subtract these from both sides of the equation. So that's going to be greater than 0.15 I2 minus 0.1 I2. So that's 0.05 I2 plus, and now I'll do the same thing for I3. 0.15, 0.1. So I'm going to subtract 0.1 from 0.15. So 0.05 I3. All I did going from this to this is I just distributed the 0.15 and I subtracted and added to simplify a little bit. And actually this is interesting too, because I just have these 0.05s everywhere. That's a positive number. And I was able to do that because I just added and subtracted from both sides. But if I multiply or divide by a positive number, then I don't have to change the inequality. And you could say, let's just divide both sides of this equation by 0.05, or the equivalent is to multiply both sides by 20. But then we're left with I1 is greater than I2 plus I3. And I think this simplification, without having read the statements, was worth it, because we went from something very convoluted and a very convoluted problem statement to something very simple. So essentially they're asking us, was the price of I1, was the price of item 1 greater than the price of item 2 plus item 3? This is, if we can answer this question, we can answer the harder question. So statement number 1. The regular price of the most expensive item was $50. I1 was equal to $50. And the regular price of the next most expensive item was $20. So I2 was equal to 20. So now the question boils down, was 50 greater than 20 plus the third most expensive item? Well, I don't know. Depends. Well, actually, this answers our question, right? Because I was about to say, well, the third most expensive item, maybe it's $30. But by definition, we know that it's not $30. Why? Because it was the third most expensive item. The second most expensive item is $20. So this thing has to be less than $20 if we are to consider it the third most expensive item. So if this thing is less than $20, then the right-hand side of the equation is definitely, it's going to actually be less than $40. So this is definitely going to be less than 50, so this is going to be true. So it turns out that statement 1 by itself is sufficient, because you just have to realize that I3 has to be less than 20 if I2 is equal to 20. Statement 2. The regular price of the least expensive item was $15. So let's see, that statement by itself, we get I1 is greater than I2 plus 15, where this is the least expensive item. So just looking at this, we know this is going to be 15. This is going to be more than 15. Yeah, this is hard. You can't say anything about this, because maybe I1 is 17, and is 17 greater than, maybe I2 is 16 plus 15. And in this case, it would not be the case. Or maybe I1 is $170. and I2 is 16 plus 15, in which case it would be the case. So statement 2 by itself isn't sufficient. So the answer to this is A. Statement 1 alone is sufficient to answer this question. See you in the next video.